Welcome to The Explainer. Today, we're going to demystify one of the most common and most powerful graphics in all of data science. By the time we're done here, you'll know exactly what an ROC curve is, how to read it, and most importantly, why it's such an essential tool for making smart decisions.
But first, let's go back in time. I want you to imagine something. You're a radar operator during World War II. You're staring at this fuzzy screen, and you have to make a call right now. Is that little blip on the screen an enemy plane? Or is it just a cloud?
You see, if you crank the sensitivity way up, yeah, you'll spot every single plane, but you'll also be scrambling your fighter jets for every puffy cloud that drifts by. But if you turn it down too low, sure, things will be quiet, but you might miss a real threat. This is the core problem, this constant trade-off that led to a brilliant invention, the Receiver Operating Characteristic Curve, or ROC curve for short.
Okay, so to really get a handle on this trade-off, we need to map out every single way a prediction can go. We're going to jump from that WW2 radar screen to a modern medical example, where, the stakes are just as high. What you're looking at here is called a confusion matrix, and it's just a fantastic way to see how a model is performing in a single glance. It puts reality, did the patient actually have heart disease, right up against what our model predicted, and that comparison gives us these four distinct boxes, four possible outcomes. So first, we've got our wins, right? The true positives, where we correctly said yes, there's disease, and the true negatives, where we correctly said nope, all clear. But then you've got the errors. The false positives, those are our false alarms, and the false negatives, well, those are the really dangerous misses. These four numbers, they are the absolute foundation for everything we're about to do. All right, so now that we have those four counts, we can start calculating a couple of really crucial rates, metrics that tell us how good our model actually is. And those two metrics are called sensitivity and specificity. Think of it like this. Sensitivity, which is also known as the true positive rate, answers the question. Out of all the people who were actually sick, how many did we catch? Specificity is the flip side. Out of all the healthy people, how many did we correctly clear? Going back to our analogy, it's about how well we spot the planes versus how well we ignore the clouds. So for our heart disease model, let's figure out this sensitivity. It's pretty simple. We just take our true positives, that's 1111, and divide by the total number of people who were actually sick, and that gives us 80%. So in other words, our model successfully found 80% of all the patients who had heart disease. Not bad. And now for the other side of that coin, specificity. We do the same thing, but for the healthy people. We take our 146 true negatives and divide that by the total number of people who were actually healthy. That gives us 89%. So our model correctly gave the all clear to 89% of the healthy patients. But here's the catch. That 80% and that 89%, that's just a snapshot. It's for one specific setting of our model, one threshold. What if we tweak the dial? What if we make it more or less sensitive? How does the performance change? Well, for that, we're going to need a picture. And this is it. This is the ROC curve. What's so amazing about it is that it gives us the entire story. It's not just one data point. It's a smooth line that shows us the trade-off between our hit rate and our false alarm rate across every single possible setting.
Okay, so let's break down exactly what we're looking at here. I know it can look a little abstract at first, but this graph is telling a really specific story about how well our model works. First, let's look at the axes. The vertical one, the y-axis, that's our sensitivity, our true positive rate. Just think of this as our hit rate. We want this number to be as high as possible, as close to the top of the chart as we can get. Now the horizontal axis, the x-axis, that's our false positive rate. You might notice it's just 1 minus the specificity we just talked about. This is our false alarm rate. And for this one, we want it to be as low as possible. We want it pushed all the way over to the left, as close to 0 as it can get. See that dashed line cutting diagonally across the middle? That right there? That's a model with zero skill. That's just a 50-50 coin flip. Any model that's even worth talking about has to have a curve that's above that line. So the goal for any model is to have a curve that really bows up and out, hugging that top left corner. Because think about it, that corner is the dream scenario. It's a 100% hit rate with a 0% false alarm rate. It's perfection. The closer our curve gets to that corner, the better our model is. Okay, so looking at the shape of these curves is really useful. But what if we have two different models and we want to know which one is better?
objectively, how can we boil this entire picture, this whole trade-off, down to just one single number? We do it with something called the area under the curve, or AUC, and the name pretty much says it all. It is literally the measurement of the total area underneath that ROC curve we were just looking at. It gives us one score that sums up the model's entire performance.
So if you just imagine shading in the entire space underneath that blue curve, the size of that shaded area, that's the AUC. It's pretty intuitive, right? A model with a bigger shaded area, a higher AUC, is just plain better at telling the difference between the positive and negative cases.
So if your model gets an AUC of 0.5, that means its curve is sitting right on that diagonal line. It has absolutely no ability to tell the difference. It's no better than just flipping a coin.
On the other hand, an AUC of 1.0, well, that's the holy grail. That's a perfect classifier. It means your model's curve went straight up and straight across, filling that entire square, and it made zero mistakes. And this really gets to why the AUC is so powerful. It gives us this single, stable score of how well a model can tell two groups apart. And this is the important part. It isn't affected by how common or rare the thing you're looking for is. That makes it a super reliable way to compare different models.
And that brings us to the final question. A higher AUC is pretty much always better, yes, but the story doesn't quite end there. The best spot to operate on that curve really depends on the real-world cost of your mistakes. And this brings us all the way back to the beginning. What's worse, missing an enemy plane or scrambling your jets for a cloud? The answer to that question is what tells you which point on the curve, which balance between catching planes and ignoring clouds is the right one for you.